Welcome to Game Theory. This is section 27 in your text on mixed strategies. So in games that we've talked about so far, players have always chosen to play the same strategy. We call this pure strategies, where they do the same move every time they play the game. However, if you're playing a game, let's say rock, paper, scissors, and you always choose to play the same strategy, let's say rock, then eventually players will catch on if you choose to play the same strategy for game after game after game. So when you're playing games, it's often good to have a mixed strategy where some percentage of the time you play one strategy and other percentages of the time you play a different strategy. And so the idea with mixed strategies is that if a strategy is a long-term idea of what's going to happen, you want to know the expected payoff if you know the strategies at different times. So let's give a scenario here. So let's suppose that player A chooses to play rock 50% of the time and paper and scissors 25% of the time in the game of rock, paper, scissors. And player B chooses to play rock 75% of the time and paper 25% of the time, and scissors never in a game of rock, paper, scissors. So this is where they choose to play rock, paper, scissors the game multiple times, and on average they choose to play these different strategies some percentage of the time over the long-term value of the game. So when we're looking at this game, we have the general payoffs for rock, paper, scissors, where rock beats paper, rock beats scissors, scissors beats paper, and paper beats rock. And we know the general strategies and the payoffs here, but we want to know the payoffs if we play the mixed strategies. And so when we're looking for the expected payoffs from the mixed strategies, we need to determine how the player B's 75-25-0 mixed strategy compares against player A's rock strategy. So what we can do is we can say that if player B plays in this component right here, if player B plays rock 75% of the time, they'll get a payoff of 0. This is player B's payoff of 0. Or rather, we can be more precise. We can say 75% of the time, the payoff will be 0, 0, where this is the payoff for A and payoff for player B. And then if we have the payoff, if player B plays paper 25% of the time, we have the payoff -1, 1. And this is our A-B payoff. And so we sum these together, and then finally 0 scissors, so we have 1, -1. One thing to note is these are payoffs, so these are not multiplication in the sense of parentheses. These are payoffs, so let's indicate these with brackets. Oops. So we can think of this as 75% of the time we'll get 0, 0, plus 25% of the time we'll get -1, 1, plus 0% of the time we'll get 1, -1. So 75% of the time we'll get 0 for A, and 25% of the time we'll get -1. So that means on average we'll get -0.25. For B, 75% of the time, we're 0.75 times 0 plus 0.25 times 1, so we get positive 0.25. So an average or mixed strategy will give us -0.25, 0.25. And we can do the same thing for this next spot when we play paper versus B's mixed strategy. So we have 75% of the time, we play against 1, -1 as our payoff, plus 25% of the time, we're competing against a payoff of 0, 0, plus 0% of the time, we would get a payoff of -1, 1. So since we're getting a payoff of 75% of the time we have a payoff, 25% of the time we get nothing, and 0% of the time we have our other payoff, we get our payoff here of 0.75, negative 0.75. And then similarly, we could do the same thing here, and we get negative 0.5 and 0.5. Players A's works the same, where we get 0, 0, and then negative 0.25, 0.25, and positive 0.25, 0.25. Here using player A's payoff strategy of 50, 25, 25. Now the question is how do you operate the expected payoff for player B versus player A's mixed strategy? And this is where we operate in the same fashion. So player B's mixed strategy versus player A's mixed strategy. We can consider in the same way that we looked at player A's pure strategy versus player B's mixed strategy. We can say 0.75 for player B right, this is B's, and we can say versus 0, 0. This is player A's mixed payoff. So just like reading along the pure strategy row, we can read along the mixed strategy row. Plus 0.25 times the strategy, times the payoff strategy, negative 0.25, comma 0.25, plus 0 times the payoff, 0.25, negative 0.25. And so what we get is we get 0 from the first component plus a quarter times a quarter makes negative 1/8, comma positive 1/8, and 0 from the second component, where this turns out to be negative 0.0625, comma 0.0625. Or we can keep it simple and just do negative 1/8, comma 1/8. So this is how we treat it as the pure strategy. We treat a mixed strategy as just another strategy. And so we operate a strategy as a row that if we're comparing a mixed strategy versus a pure strategy, or a mixed strategy versus a mixed strategy. Once we have that strategy's payoffs, we can just compare it in the same way. And so what this does is this gives us the expected payoffs of any combination of mixed strategies versus mixed strategies. So let's do another problem here. Let's suppose that we have another payoff matrix here, where we have left, right, up, down for the player choices, and we have these particular values in here. So if our goal is to find any pure and mixed Nash equilibrium, let's look first for pure equilibrium. So if A plays up, B's best response would be to play right. If A plays down, B's best response would be to play left. If B plays left, A's best response is to play up. If B plays right, A's best response is to play down. So note, there are no pure Nash equilibrium points. So before this point in the semester, we would just leave this problem alone and we'd say there's no pure Nash equilibrium points and we move on. But now we can continue and look at for mixed strategies, where at some points in time we would play one side, or we would play one strategy, and some percentage of the time we would play another strategy. So let's let P be the probability that A chooses to play up, and 1 minus P is the probability that A chooses to play down. And Q is the probability that B chooses left, and 1 minus Q is the probability that B chooses right. We don't know what P and Q are, but we can solve for P and Q with this problem. And this is a whole idea before. With rock, paper, scissors, we wanted to solve for how often you play each particular component, but we wanted to start simple and just do a 2x2 matrix first. So if I've repeated the matrix down here, so if B moves left with probability Q, then if A moves with a pure strategy U up 100% of the time, the expected value, A's expected value of playing U would be equal to 90% of the time, or they get 90 points times Q% of the time, because Q% of the time B is playing left, plus 1 minus Q% of the time, they would get 20 points. So we get 90Q minus 20Q equals 70Q, so we get 20 plus 70Q. If A plays down 100% of the time, we get 30Q plus 1 minus Q times 60. And this works out to be 60 minus 30Q. So again, the expected value for playing a particular pure strategy. So if a player chooses to play only one strategy, the expected value for that strategy depends on how often the other player chooses to play their strategies. So if player B chooses to play left none of the time, so if Q is 0 and played right all of the time, then player A would expect to get 20 points. And this makes sense because player B would choose to play right. So the question is where do these two lines intersect? We think of these as linear equations. If we look at 20 plus 70Q, if Q is 0, we start here. And if Q is 1, we're up about here. This is at 70. So this is our line here, where this axis over here is A's payoff, the expected value for A. So the expected value for A for this first line here, this is the expected value A for U. It increases. Now the expected value for A, if we look at as it decreases, we look at the other line here, this is our expected value for A if A only plays down. And what we're really interested in here is this intersection point, and we call this Q star. And this Q star point, this is the value where A doesn't care which strategy to play. Because on either side, A would get more points if B chose to play Q higher than Q star, A would choose to play up. If B chose to play Q lower than Q star, then A would choose to play down to get a higher expected value. So if B chooses to play at Q star, then A doesn't matter. It doesn't matter what A chooses to play. And so what mixed strategies, what we're solving for is A and B are each trying to determine where each other's Q star and P star are. So what the probability that each other will play these particular moments in time. And so this amounts to solving two equations. And so we can look at this graph and we can look for the intersection points, or we can set these two equations equal to each other. So I've written these equations down here. And so we've got 20 plus 70Q. This is our E sub, the expected value of A moving up is equal to the expected value of A moving down. So we set these two equations equal to each other, subtract off 20 from both sides. So we get 70Q is equal to 40 minus 30Q. Add 30 to both sides. So we get 100Q is equal to 40. Divide both sides by 100. So we get Q is equal to 4/10, which is equal to 2/5. So if Q star, this is our special point, equals 2/5, if B chooses this particular value, and this means 1 minus Q star equals 3/5, this is our choice for the probability that B chooses left, and this is the probability that B chooses right, then this will be the particular special point where A won't have to make a decision. And we can use these equations for B's payoff to solve for A's strategies. So now let's keep this in mind. So we're going to hold this Q star and 1 minus Q star. We're going to hold this in our heads for a little bit. And we can do the same thing to solve for P star for A's strategies. So we have the same setup as before. And so we see that the expected value for B playing left is equal to 10P plus 70 times 1 minus P, which is equal to 70 minus 60P. The expected value for B playing right is equal to 80P plus 41 minus P, which is equal to 40 plus 40P. We set these two values equal to each other, EB, the expected value of B sub L. This is 70 minus 60P equals 40 plus 40P, which is equal to the expected value of B playing right. We can add 60 to both sides. So then we get 100P, so 40 plus 100P equals 70. Subtract off the 40. So we get 30 is equal to 100P. So P equals 3/10. One thing to notice is these are probabilities, so they should always fall between 0 and 1. And that's a good check for yourself. If you get a probability bigger than 1, you know you've done something wrong. If you get something that's negative, you've also done something wrong. So we know that P star is equal to 3/10, and 1 minus P star is equal to 7/10. So P star is equal to the up, and 1 minus P star is equal to the down. Those are the probabilities that A will choose up and down. So now we've got the probabilities, now we just have to find the payoffs corresponding to the mixed strategies. So what we've done is I've pulled the P star and the Q star. So here's our P star and our Q star, and I've pulled the expected value for A from either equation, either the up or the down. In this case, I pulled the expected value for A using, so to this particular equation here, this is the expected value for A, excuse me, using the, where'd you go? Expected value for A, assuming that B plays left. And this is the expected value for B, assuming that A plays up. So you can use either expected value formula for the player. You could use either for A, you could use a payoff for either left or right if B chooses left or right. For B, you could use up or down if A chooses up or down. You're just looking for the expected value for that player. And you substitute in that Q value. And so what you get is you get that 20 plus 70 times 2/5, that special point in time, is equal to 48. And the expected value for B would be 70 minus 60 at 3/10 would be 52. So at this particular point in payoff, so if A chooses to play 3/10 up, 7/10 down, and B chooses 2/5 left and 3/5 right, then the expected value of payoff has 48.52. So the players can expect that this is the mixed Nash equilibrium point. And the indifference theorem says that a mixed strategy for player A is a best response to the mixed strategy for player B if each strategy for A, each pure strategy for A, the pure strategy supports the best response to the mixed strategy for B. And here the idea of supports, this means that the intersection point on the graph, intersection point, if the intersection point on the graph is that pure strategy, that intersection point is the best point on the graph, that the intersection point holds. So the next video, we'll do a couple more examples of mixed strategies. So as always, if you have questions, let me know.